We are going to be graphing exponential growth and exponential decay functions with and without shifts. The way that we graph exponential growth and exponential decay functions is done specifically to help prepare us to graph the inverse of these functions, which is a logarithm function. With an exponential function, we can use our calculator to check to make sure that we have the process down and we understand how to do it. Because with a logarithm function, we do not type those into our calculator to graph. We actually have to walk through the process of applying each transformation to the logarithm. Now, what is an exponential function? It's a function that has a variable for an exponent. And when we graph these exponential functions, we introduce the concept of having an asymptote. Now, the graph that's actually there with Gandalf does not represent an exponential function. It's actually a rational function that we'll talk about later in chapter 8. But with this exponential function, the asymptote still has the same rules as an asymptote in a rational function. That's that dashed line here. That's our asymptote. And Gandalf is representing what an asymptote really is. It's a line that our graph cannot actually touch or cross it. It will approach it, but then once it gets there, it kind of acts almost like a magnet, two magnets with opposite pole or with the same polarity. It'll move along it, but it will not actually touch it or cross it. And I'm giving you kind of an anchor chart here for our exponential functions. This is just a simple exponential function, y equals b to the x. That's what the graph is, but it does give us some guide points that we're going to use to apply different transformations to it. And those are listed here. Here's the equation for an exponential function. And this should look similar to what we've seen before when we had h and k in quadratics or radical functions, or all the way back at the beginning of the year with absolute value functions. Our a value will represent a reflection if it's negative across that y equals k line. And when the absolute value of the a, because remember the negative tells me reflection, so we're only dealing with the absolute value now. When that absolute value is greater than 1, then it will be stretched vertically, meaning it'll get bigger quicker. When the absolute value is between 0 and 1, then the graph will be compressed vertically, so it'll be more flat. Our b value is the base, and we use that b when we find the guide points. That's what the b is in our guide points. H and K tell me translation. H tells me if it's moved left or right. And remember, H is always the opposite sign of what it appears to be in the equation. And then K tells me vertical translation. It tells me how much it moved up or how much it moved down. So we can see from the graph here, we can pull some important pieces of information. First being the guide points. This is what the points would be if there was no H, no K, or no A value, meaning no transformations happening to it. And our horizontal asymptote, in this case, since there's no transformations happening to it, our k value is 0. That's why the x-axis serves as our asymptote here. So we would say y equals 0. Otherwise, for any other transformations, we just say it's y equals whatever the k value is. Domain and range follow the same pattern throughout all exponential functions. Your domain will be all real numbers, and your range will be that y is either greater than k if your line happens above your asymptote. But if there's a reflection that's happened when your a value is negative, then it'll be less than k. Your graph will be below your asymptote. Let's actually walk through how to do a couple of these problems. We'll turn the page. The one thing that I didn't talk about was how to know whether something was exponential growth or exponential decay. And that also comes from my b value. If that b value is greater than 1, then we say that this is exponential growth. And if our b value is between 0 and 1, then we say it's exponential decay. So our first step in even figuring out that would be to list out all of the pieces from the graph. We have a b value of 2. It's our base for our exponent. We have an a value of 3. And because there's nothing added or subtracted to the exponent, our h is 0, and there's nothing being added or subtracted outside of the exponent, so our k is also 0. Since our b value is greater than 1, we will indicate that this is exponential growth. And we can go ahead and list out our points in our table. So if there was no 3 there and our h and k remained at 0, then this would be the points that we would plot to graph our equation. We have 1, 0, and -1. Those are our x values. And our y values would be b, 1, and 1 over b. I find it easier to list all the x's first because they follow that pattern, 1, 0, -1, and then the b values after that, b, 1, 1 over b for our y values. When we apply each transformation, the application comes from what that is actually doing to the graph. We talked about our a value being the stretch. It's either being stretched vertically or made flatter. And so because it's happening vertically, we apply it only to the y. So in order to get the transformation applied, we multiply all of our points by a factor of 3 for the y value. So our x values will remain the same, 1, 0, and -1, but our y values will each get multiplied by 3. So 2 times 3 is 6. 1 times 3 is 3. 1/2 times 3 is 3 halves. And then h and k. H, since it's a horizontal translation, we would only apply it to the x value, and k is a vertical translation, so we only apply it to the y value. Since both h and k are 0, we don't need to actually add anything to the h value, and we don't need to add anything to our y value as well. So I just draw arrows to indicate that it kind of zooms past that step. Now, whatever points are in the last column or the last place that you wrote down the points are the ones that you need to plot. Before you go plotting, you need to also identify your asymptote. Remember, that comes from our k value. So our asymptote, we'll use ASY to represent asymptote, is y equals k. Always make sure that you're writing this as an equation because it represents a line. Putting only 0 for asymptote does not indicate that you know that it is a line that goes through y equals k. So I plot my point or my asymptote first. I'll use a dashed line for my asymptote. And then we'll plot our points. So we have one at 1, 6, one at 0, 3, and finally -1 and 3 halves. And we can see it trending downwards. And the beauty of being able to do our exponentials in the same way that we're going to need to do them for the logarithms is that I can actually type this into my calculator and check to make sure that it is correct. So we're going to do that now. We'll type 3 times 2 to the x into our y equals. And when I head over to graph, I'll see that really it does extend along my asymptote and continue upwards. Now be very, very careful because if you look at this, it looks like it's actually touching this y equals 0. But we know because we are able to find our asymptote that it does not actually touch that line. So your calculator can be deceiving, and again, it's just a tool, but it does have limitations. So you need to know that the asymptote does not touch the line. Make sure that I can see a bit of white space in between where you drew your line and where you drew your asymptote. If you're afraid that your line is too close to your asymptote and that I won't be able to tell that there's white space there, I do ask that you write me a note next to it just saying this line does not touch the asymptote. Now, if it's clearly going over the asymptote, your note is not going to be enough to indicate that you knew what this graph should have looked like. I usually like to draw along the asymptote first And sometimes it'll look like a straight line. That's okay. And then go up through my points or down through my points, wherever I'm drawing. We need to list our domain and our range. Remember, all exponential functions, the domain would be all real numbers. And the range, we have y, in this case, is greater than, because it's on top of the asymptote, our k value, which is 0. Oops, and I forgot to write the 0 when I wrote my asymptote. Y equals 0, our k value. Let's take a look at another one that has some h and k to apply. So our first step, we're going to label our b value. Remember, that's the base for the exponent. So b in this case is 4/5. Then we'll label our a, which is -1/3. We'll label h next. Remember, h is always the opposite of what it appears to be, so +4. And then k is 3. Since our b value is between 0 and 1, we can indicate that this is exponential decay. And let's apply our transformations. We have 1, 0, -1, and then b, 1, and 1 over b. Since b is a fraction, it can get a little confusing to write 1 over 4 over 5. Just know that when we say 1 over, what that's really saying is reciprocal. So this should be 5/4. Now you can always double check that on your calculator by typing in 1 over 4/5 and changing that to a fraction, and you'll get the reciprocal 5/4. Let's apply our first transformation, which is our stretch and our reflection. We'll multiply each of our y values by -1/3. So our x values will remain the same. And then our y values will get multiplied by -1/3. So we have 4/5 times -1/3 gives me -4/15. 1 times -1/3 gives me -1/3. And 5/4 times -1/3 gives me -5/12. Next, we're going to add our 4 to each of our x values. That means that all of our y values are going to stay the same. I like to write everything that stays the same first, so I can focus on what I need to perform in the way of operations. So 4 plus 1 gives me 5. 4 plus 0 is 4. 4 plus -1 is 3. And finally, we'll need to add 3 to all of our y values. Now, since they're fractions, you're going to need to have common denominators. I'm not asking you to do that by hand, though. You can simply put it into your calculator. I do ask that you write them as fractions, though, when you write them in the table. The decimal can be helpful, though, for calculating or for figuring out where to plot them. Remember, math frac will change it back to a fraction for you. So we'll write all of our x values down, which is 5, 4, and 3. And then our y value. First is 41 over 15. Next one, we'll need to do -1/3 plus 3. Change it back to a fraction. And finally, we have -5/12 plus 3, and change that back to a fraction. So when I actually go to graph these, I need to list my asymptote first. Which is y equals my k value, 3. And we'll plot that with a dashed line. And then plot our points. So we have 1, 2, 3, 4, 5, and 41/15, which we saw on our calculator a minute ago, was 2.7. Then 1, 2, 3, 4, and 8/3, which we saw was 2.6. And then 3 and 31/12, which we just saw was about 2.58. Now that looks like they go pretty much in a straight line, with the biggest being to the right and the smallest being to the left. Recognizing that the biggest one was to the right indicates that I'm going to have my line moving along the asymptote here, and then it'll continue downwards. But remember, we have our exponential equations, the ability to type them into our calculator and look at the graph if we're unsure of what the shape is supposed to look at, especially when you are just getting used to typing or to graphing these kind. So I've typed it into my y equals here, and I'll just hit graph so I can take a look at it. Oops, it looks like I forgot to type in my k value at the end. So we can see as we approach that y equals 3 that it's moving along y equals 3 here. You can also check your numbers in your calculator by going to your table. So if you need the decimal form, your table can give you those decimal forms. So it moves along here and then continues downward. Next one, we need to list our B, A, H, and K. B is 4. Our A is 2. H, opposite sign of what it appears to be, 1. And K is -6. Since B is greater than 1, that tells me that this is going to be exponential growth. And we can list out our guide points. 1, 0, -1, B, 1, 1 over B. Now we'll multiply all of our y values by 2. So I'll jot down my x values because they're just going to continue on. So multiplying by 2 gives me 8. 1 times 2 is 2. And 1/4 times 2 is 1/2. Then we need to add 1 to all of our x values. So that means all of my y values are staying the same. You don't have to copy the y values over first, whichever one makes more sense for your method. 1 plus 1 is 2. 1 plus 0 is 1. 1 plus -1 is 0. And finally, we'll add -6 to all of our y values. So x's will remain the same, and the y values will add -6. So we'll have 2, -4, and this one will change to -5.5, which is 11/2. Our asymptote is y equals -6. 1, 2, 3, 4, 5, 6. Dashed line. And then we'll plot the points. 1 at 2, 2. 1 and -4. And then 0 and -11/2 or 5.5. So it's going down and getting closer and closer to this y equals -6. So it's moving along the asymptote here, and then a very sharp incline. Our domain, and it looks like we forgot to list our domain for our previous one, so we'll have to go back here. Our domain is all reals because that's what a exponential graph has. And our range, since it's sitting on top, by is greater than our k value, -6. For the previous one, we forgot to list our domain and range. Domain, still all reals. And range, y, is in this time it's below the asymptote, so less than our k value, which is 3. Let's do another one. B is 3 or 2/3 in this case. Then our A value is 3. H in this case, opposite of what it appears to be, so positive 3. And K, there is not anything for K, so it's 0. Since that 2/3 is between 0 and 1, this is exponential decay. And we'll list out our guide points. 1, 0, -1, 2/3, so B, 1, and 1 over B. Remember, when it's a fraction, 1 over B is just the reciprocal. Let's multiply all of our y values by 3 because that's our a value. So 1, 0, and -1 will remain the same. 3 times 2/3 is 2. 3 times 1 is 3. 3 times 3/2 is 9/2. If you're not sure how to do them by without a calculator, that's okay. You can just type them into your calculator. Then we need to add 3 to all of our h's. So that means add 3 to all of our x's. All of our y's are going to remain the same. Three plus 1, 3 plus 0, and 3 plus -1. And finally, adding 0 to all the y's, which doesn't change anything. Notice how each time, once I've applied a transformation, I never go back to the first here. That's why we continue to copy over the ones even if they don't change. So we'll go ahead and plot our points and our asymptote. Our asymptote in this case would be y equals 0 because that's our k value. And we'll plot the points at 4, 2, 3, 3, and 2 and 9/2, which is about 4.5. So it's trending downwards, so it's going to move along the asymptote over here and go up through our points. Domain, all real numbers, because it's an exponential. And the range, y is, since it's on top of the asymptote, is greater than our k value, which is 0. I believe we have one more example. Listing out our B, A, H, and K. B is 3. This time my A value, there isn't one listed, so it's just 1. H is positive 2, and K is 4. So when I list my guide points, I have 1, 0, -1, and B, 1, 1 over B. To multiply everything by the y's by 1 doesn't change our y values. Since our b value is greater than 1, it is exponential growth. And we can add 2 to all of our x values. That means that all of our y values are staying the same. 3, 1, and 1 over 3. So each of our x values will get added 2. So 1 plus 2, 2 plus 0, and 2 plus -1. Then we need to add 4 to all of our y values. That means our x values are going to remain the same. 3, 2, and 1. and our y's. 3 plus 4 is 7. 1 plus 4 is 5. And 1/3 plus 4, and you can use your calculator if you don't want to find common denominators in your head. And we get 13/3. Make sure you list it as a fraction. Our asymptote would be y is equal to 4. So here's my dashed line. Three, 3. Oh, sorry, 3, 7. We want to use the ones from the last column here. 2 and 5. And 1 and 13.3 repeating is 4 and some change. So that means it's going to continue along our asymptote over here on the left and then up through our points. Domain still remains as all real numbers. Our range, y, is greater than our k value, which is 4, because it's sitting on top of our asymptote.